This is section 13.6, and this is the introduction of surface integrals over vector fields. So we just talked about orientation and the uh, normal vector, the unit normal vector n that is pointing outwards from a surface. And so now we're going to talk about the idea of this surface integral we've been studying in this section and over a vector field. So as a quick review, if we have a line integral of a vector field, F, that can be interpreted as the work done by the force field F on a particle moving along a path. In a similar way, a surface integral of a vector field, if we have a vector field that represents, for instance, fluid flow, then the surface integral will represent the amount of fluid flowing through the surface. And you could think of it almost as like a net, fishing net being dragged through the water, and the measurement that we're taking is the fluid flow that goes through that particular surface. If the water is flowing at a perpendicular direction to the surface, then a lot of water is going to flow through the surface. However, if the water is flowing along the or parallel to the surface, then there will not be water that will flow through it. The flux, this type of integral is called a flux integral. So when we talk about, for instance, in this statement about the fluid flow through the surface, we could say that the flux will be large. That's just another way of representing what's going on here with the surface integral over a vector field. So if it's parallel, then that flux would be 0. So to calculate the amount of water that flows through the surface, we're going to add up the component of the vector F that is perpendicular to the surface. So in other words, if we're looking at this picture over here, this graph, we have a normal vector. And remember, the normal vector is going to be really just represented by, if this surface here is r of uv, let's say, then if we take the vector r of u and cross it r of v, so these partial derivatives, then that's going to equal not necessarily n, because remember n is going to be a unit vector, but it will be some scalar of it. So let's say that we multiply by c or something like that, where it might not be 1 unit in length, but that's really what's going on with n. So this vector n, that vector is going to be perpendicular to the surface, and we get that vector by taking the cross product between these partial derivatives, and there will be a scalar element to it. But anyway, the idea here when we're looking at water flowing through the surface is that we want to add up the component of the vector F that's perpendicular to the surface. So in other words, if the vector F, if that force at that particular spot is in the exact same direction as n, well, then the angle between them would be 0. And this goes back all the way to chapter 9 and the component feature. But anyway, if F points away from n a little bit, we want to know how much of F is impacting n. And if you think back to when we were looking at the components in chapter 9, we maybe could draw this a little bit better if we just drew this out as F and n. And what we're looking for specifically is, if we drop this down, what is this amount right here? Because we want to know what is the vector F's impact on vector n. And so what we could do is take our dot product formula. So we have, and this is the angle, by the way, so we have n dotted with F, and that's equal to the magnitude of n times the magnitude of F times the cosine of the angle between them. Remember that the magnitude of n, since it's a normal vector, is simply 1. So this is 1. And this little bit right here, that is going to be representative of this distance in black. So let's just call that x. So that distance right there. So x is going to be equal to the magnitude of F cosine of that angle. And what this means, and I'm just going to write this out again. So x is equal to the unit vector n times the vector f. And so if that represents the amount of f onto n, then what we can do then is integrate this, and what we get is the amount over the entire surface. So we're going to take, this calculation, and we're going to total it up, and that's what you see in our formula right here. So the surface integral, again, now is over a vector field. So we have a vector f, we have a vector s, and we can convert that because when we look at our operator, so this is ds, and notice that it's very similar to what we have done earlier in this section, but earlier in the section, the ds that we utilized, that s was not a vector. That was just ds. That was just a surface integral, not over a vector field. It was just simply a surface integral. Now, again, we have this vector f and we have a vector s because this surface is over a vector field, and we need to turn this into just a simple ds. We don't want it to be a vector, and so what we do is we utilize the idea that the length we're looking for is simply the vector f dotted with the vector n, and then we're going to just integrate that over the entire surface S. And remember, this is called the flux of f across x. So if they ask you to calculate the flux, that's what they're asking for there, okay? Now, obviously, based on what we have done in the beginning portions of this section, to calculate this type of an integral is a little bit tricky. We don't really want it to be ds. We want a double integral to be dA, for instance, because we want to be able to calculate this based on, let's say, x or y, or based on some other set of variables. We have like r of uv. We want to be able to do this in terms of something that we're familiar with. So just recall from when we first started this in the beginning of this section, ds, where ds was not s was not a vector, it was just a simple integral operator. ds was equal to, if you remember, we converted this to dA by taking the magnitude of the cross product between these two vectors. So you can kind of go back to the beginning of the section if you want to, but that was what ds was. Now, if we take and look at what we have here in our integral, so the vector n times ds, what actually is vector n? Well, if we go back up here for a minute, so vector n is the unit vector that is given by the cross product between these two vectors. And so I had mentioned that it's a scalar there. Well, we can write it more completely by saying that n is really the cross product between these two vectors divided by the magnitude of those vectors. That's what would actually produce vector n. So if we kind of put all this together, if n is going to be the cross product between these two divided by the magnitude of that cross product, and ds is the magnitude of the same exact cross product times dA, well, then what happens algebraically is that we cancel those magnitudes, and what we get is a nice double integral over a region D with a dA operator, where we're able to calculate the surface integral over a vector field. Now, again, we're adding many formulas here in this entire chapter, and this is just yet another one. And so there is some complication to be able to know which one to use, and hopefully as we continue to practice, you'll be able to make some sense of that. But this is going to be a vector f dotted with a cross product. And remember, this is not the magnitude of a cross product. This is simply a cross product between two vectors, which means we get a vector here. So we're doing the dot product between two vectors and then dA. And remember, the region here is going to be the thing that will change problem to problem. We might be able to change variables, or we might be able to do something with that to make more sense of it. But this is a very important formula for us. Now, the next page in the next video, what we're going to do is talk about what if the surface itself would be better represented in X, Y, and Z. And so if that's the case, then we'll have a slightly different formula, of course. This formula is best utilized when you have the surface in a vector form. So the vector r of, let's say, u and v, and u and v are dummy variables.